Hello again. We're going to talk about the last 3 lessons of this year's training material in the chemistry book. It's lessons 29, 30, and 31. They all have to do with gases. But before I can get into detail about what gases do and don't do, I'd like to remind you about the 3 states of matter and how their molecules act depending if they're a solid, liquid, or a gas. So right now I'm going to write up on the whiteboard the 3 different states of matter: solid, liquid, and a gas. A gas is also known as a vapor. And if I just used water as an example, because every substance is capable of going through all 3 phases. If water was a solid, we called that ice, and we would see water molecules very tightly packed It's my ice cube in all 3 directions. They're so tightly packed, they're not moving other than vibrating. They are stuck together by their intermolecular forces. One molecule bonded to another molecule is a very strong attraction force, especially with water, because there's hydrogen on one end of the molecule and oxygen on the other end. That's called a hydrogen force. Your intermolecular forces are very strong. These molecules have a definite shape. If I put this ice cube into an empty glass, it's still going to stay the shape of a cube. They are very tightly packed molecules. They have a lot of potential energy in them. Potential energy is how much energy you have stored up, ready to use. Kinetic energy is the energy you are using. So let's say you ate a whole plate of spaghetti. Now you're feeling tired and lazy, you're just laying there, but you've got a lot of calories in your stomach. You've got a lot of potential energy that you could use up later on when you go for a run and you're feeling more comfortable. But while you're running, you are using that energy, and that's called kinetic energy. Molecules in their solid state have a lot of potential energy. Liquids, on the other hand, they are also, if you can imagine a puddle of water right now, you also have water molecules that are tightly packed, but they have absorbed enough energy to flow where they're not so rigid like the molecules are in a solid. This particular molecule, if it wants to move over here, it can. It just kind of slides by and rolls by the other one. So we don't say a liquid has a definite shape. If I took some liquid water and I put it into an empty cup, the liquid water would take the shape of the container. They're packed, and they're pretty tightly packed, but they're not as rigid. They're more fluid. So I'm going to say they flow past each other, or they're fluid. They have quite a bit of potential, but they also are using some kinetic energy here also. So you're going to see a bit of potential energy plus kinetic energy when you are looking at liquids. When we're looking at water as a gas, those are just individual molecules. So far apart from each other, there's no attraction force whatsoever. You've seen that with steam. When you boil a pot of water and you see the steam coming out, those were liquid molecules that have broke their intermolecular forces, and they have become individual gas molecules. They do not have a definite shape. Whatever container I put that gas in, it will take the shape of that container. It will fill up that container. So if I opened up my hand and a bunch of gas molecules evaporated out, they would move and take up the whole space of this room. They'd be as far apart as possible in filling up the room. So these guys just fill the container they're in. It could be a bottle, it could be a whole room. We also call gas molecules fluid because they can flow, and that's what fluid means. They can flow past each other, so they're very fluid, and they have a ton of kinetic energy. Kinetic energy is the motion energy. So the three different states of matter, one substance like water can exhibit all three states. What we're going to start studying in lessons 29, 30, and 31 is more about gases. What happens with gases? What things affect gases? What can we do with them? So, you don't have to watch me erase. So let's just focus on gases. There are some things you should know about gases. We have this thing we call an ideal gas, but it's so very close to the real world. An ideal gas, is a substance of vapors where the molecules are not attracted to one another. We say an ideal gas would have a molecule of that gas and a molecule of this gas. They would just float by each other and they'd say, hey, hi, how are you doing? And just keep on going. That there's no attraction force between one molecule of a gas and another molecule of gas. But the real world is, if you have a polar molecule and another polar molecule of gas, as they're floating by each other, they might say, ooh, and there might be an attraction force. But in the ideal world, we say, nah. We say they just keep traveling right past each other. Another thing we say about an ideal gas is that that gas molecule is moving with all that kinetic energy, and it's moving and it hits the wall and it bounces back off of it. We say that that ideal gas molecule did not lose any energy falling into that wall and bouncing back. But imagine if you yourself fell into the wall. You would not bounce back with the same speed you hit it because some of your energy was lost into the wall and you might fall down right here. But we say a gas molecule is so small that it doesn't get affected. If it's traveling really fast, it hits the wall, it bounces right back. And in the real world, it's close to that. It's almost that. So we ignore the little bit of energy that little bit of molecule might lose when it does hit the wall. That's part of an ideal gas. Another thing we say about an ideal gas is that they're always in motion. And you know what? That's real gases too. We also say the temperature of a gas is dependent on its kinetic energy. And that's true with the real world gas too. So though you may hear the phrase ideal gas versus a real world gas, there's just minor differences, and those little differences will not influence any calculations you make about your gas. So we base our mathematics and our calculations off of the ideal gas principles. That's why I shared that with you. Something I want you to know is in the practices of ideal and real gases, we've talked about kinetic energy and how the temperature influences the kinetic energy. Do you know what temperature measures? Think about that. What does temperature measure? Most people will tell me if it's hot or cold outside. But hot or cold compared to what? The real definition of what temperature measures is the following. Temperature measures the amount of kinetic energy. Remember, kinetic energy is the motion energy. So now when you tell me, hey, it's hot outside, I'm going to say, how hot? You might say 80 degrees. Well, an 80-degree day compared to a 30-degree day is a huge difference. On an 80-degree day, you and I have a lot of energy. We're out walking the neighborhood. We're playing softball. We're doing all kinds of fun, active events. On a 30-degree day, we're staying home. We're not moving. We're cold. We're trying to stay warm. So temperature measures the amount of kinetic energy. Think of it that way. The more motion you have, the higher your temperature will be. The less motion you have, the lower your temperature will be. And that is the difference between a 30-degree day and an 80-degree day. what they are measuring is the kinetic energy of the air molecules. Air is a gas. So when we talk about the temperature of the day, we are really talking about how much kinetic energy the air has, how much motion is happening in those gas molecules. Okay, when we talk about gases, obviously now temperature is one of the key things we'd like to know about. In the formulas I'm going to present to you, the temperature we must use is Kelvin. Kelvin is just another unit of measuring temperature. You and I are very familiar with the Fahrenheit scale. On the Fahrenheit scale, at 32 degrees Fahrenheit, we know water will freeze. We know at 212 degrees Fahrenheit, water will boil. On the Celsius scale, water will freeze at 0 degrees Celsius. Water will boil at 100 degrees Celsius. Well, if we are talking about temperature measuring the amount of kinetic energy, you and I have experienced days here in Michigan where we're at negative 15 degrees. You've heard of a negative 10 degrees Celsius scale. If temperature measures the amount of kinetic energy, how can you have negative energy? I get it. If you have no energy, you've got zero energy. I get that. But how do you have negative energy? You don't. And a guy named Kelvin brought that to the scientists' attention. And he said, you can't measure temperature with negative numbers. Because I understand the accuracy of the Fahrenheit scale. Because think about this. Between 32 and 212, there's 180 gradients of it. Gradients. On the Celsius scale, there's 100 different gradients. So if you're measuring something, let's say that the thermometer comes up to this value right here, well, you come down, you look at the Fahrenheit scale, you're pretty accurate as to what that actual degree is. When you go to look at the Celsius scale, it's somewhere between 2 and 3, maybe 2.5, maybe 2 3/4. So you get a more precise reading on the Fahrenheit scale. Totally get that. And the Celsius scale is built off of water. But Kelvin was saying, how can you have negative energy? You can't. So what he did is he figured out on the Celsius scale, because that was the one that was being used most widely, not that it was the most accurate, but was used most widely in the world. He figured out on the Celsius scale when there was absolutely no more energy. And he found that to be negative 273 degrees Celsius. So all Kelvin did was he created another temperature scale using the same gradients, the same size distance as the Celsius scale, but he started his at 0. He doesn't call it degree. He just, last initial, K. 0 K. He said 0 on the Kelvin scale is the same thing as negative 273 on the Celsius scale. So, if you are at 0 degrees on the Celsius scale, you must have been at 273 on the Kelvin scale. Because whatever your Celsius degree is, if you add 273, that will equal your Kelvin number. Right? If my Celsius was negative 273 and I added 273 to it, I'd get 0. And that's what he did. He took 0 degrees Celsius, added 273 to it. So if I was at 22 degrees Celsius, which is about room temperature, I would be at 295 on the Kelvin scale. So, temperature is something that's very important as we talk about gases. The key thing you have to know is every formula I share with you from this point forward to the rest of the chapter, your temperature must be in the Kelvin unit. To get to Kelvin, you take your Celsius degree and add 273 to it. Got it? Okay. If your temperature is known, or even if it's not known, another thing we like to know about our gases is what pressure is it under? And pressure is a unique thing. Pressure can be measured in so many different units. Now remember, temperature must be in Kelvin when we're talking about gases. Pressure can be in many, many different units. So I'm going to share a story with you. It is not factually true, but it is something that helps you memorize things. It says the pressure, which is the force that gets applied over some given area, has many different units. And how to measure that pressure for gases, when many times you can't see gases, here comes my story. A guy named Bruley. Since gases are hard to measure because you can't see them, a scientist had an idea. Here's what he did. Here's the story. So pretend that there's a mountain and it comes down to the beach and then the seabed filled with water. Well, you and I know that water molecules are tightly packed, but they're fluid. And we know that one water molecule could possibly flow past a water molecule on the top of the surface and all of a sudden become a gas molecule. So we could have a few of these water molecules escaping. And we know they're out there moving with much more energy and more speed than the liquid molecules. Well, this scientist was wondering if he could figure out what the pressure would be of those gas molecules as they come down and they hit the beach, or they go sideways and hit the side of the mountain. So he came down to the beach one day and he had a tool in his hand. He created this tool. He called that a barometer. And this tool was just like a board, and he let the gas molecules around it hit it and bounce off of it. And then when he looked back at his board, which he had numbers on them, like 0, 1, 2, he noticed the needle on his board was pointing to 1. So he said, being down here at sea level, my board is reading the number 1. Because I've got to make up a unit for my board, though. So he said, since I am standing on the Earth, and I know the first layer of gas around the Earth is called the atmosphere, I'm going to make up my own unit, and I'm going to say that the water vapor or gas molecules that are at sea level have a pressure of 1 atmosphere. That was great. And while he was doing his experiment, his buddy came with him, and his buddy decided to climb up the mountain and take a little break, and he sat down here. But his buddy that walked with him had a bowl of mercury, a very large bowl. And he set the bowl of liquid mercury down on the beach while he went hiking up the side of the mountain. So there's your liquid mercury in there. And when he went to sit down, he had a test tube in his back pocket. So he threw the test tube out, and coincidentally, that test tube that had a bunch of scales on it landed upside down inside this test tube. So here's his scale on his test tube. And he was just watching his buddy do his experimental work. While he was sitting up there watching, he noticed that the mercury was being pushed up the tube to a certain height. He's like, hey, look, the air molecules that are over here that are also moving and hitting the surface of my liquid mercury are pushing it up a tube. So he hurried down the mountain and he looked to see, and he read that the mercury was pushed up to a height of 760 millimeters of mercury. So that's how you write that, 760 millimeters of mercury. And his buddy said, hey, my device is reading 1, and I made up a unit called atmospheres, which I'm going to abbreviate to ATM. He said, so basically we have created 2 ways to measure gas pressure now. How much force the gas molecules put on a certain amount of area, 1 unit for pressure to measure it is ATM. And at sea level, that pressure is 1 atmosphere. And his buddy said, hey, well, that would be the same thing if you had a bowl of mercury and it pushed it up 760 millimeters on your test tube. So these both equal what the vapor pressure will be at sea level. Interesting, huh? Now that's just a made-up story. But this guy, his friend, his name is Torricelli. So initially when this work happened, he didn't call it 760 millimeters of mercury. He wanted to claim some fame. So he said that that was the same thing as 760 torrs. So 760 torrs is the exact same thing as 760 millimeters of mercury, which is the exact same thing as 1 atmosphere. There are other units of measurement too. You have heard of PSIs. 14.7 pounds, which is a unit measurement for force, per square inch, which inches squared is a unit for area. 14.7 pounds per square inch is also the same pressure of gas molecules at sea level. It's the same thing as 101.325 kilopascals, which is the same thing as 101.325 pascals. And believe it or not, the SI, the International System Standard for pressure, is actually the Pascal unit. 101,325 pascals is the same thing as 1 atmosphere. It's the same thing as 14.7 psi. It's the same thing as 760 millimeters of mercury. And in the chemistry world, we use ATM and millimeters of mercury more than anything. But you should know all of these. They are all equal. So guess what you do when you know 2 things are equal? Convert. So if I gave you, let's say 800 millimeters of mercury, and I wanted to know how many atmospheres that was, you would do the basic converting we've been doing all year. You would write 800 millimeters of mercury, put it over 1, multiply it by a fraction bar, 2 things that are equal. You want to cancel the millimeter of mercury unit, so you put that on the bottom. You want to go to atmosphere, so you put ATM on the top. You find the 2 numbers that make those equal. 1 atmosphere is 760 millimeters of mercury. And when you throw that into the calculator, your millimeters of mercury will cancel. And you'll get 1.05 ATM. So it shouldn't matter what unit the pressure is given to you in or what unit you want it in. If you know all of these things are equal to each other, you should be able to convert from one to the other. I could have given you 800 millimeters of mercury and asked you how many kilopascals that was. I would write 800 millimeters of mercury, put it over 1. I'd multiply it by a fraction bar. I'd put millimeters of mercury on the bottom and kilopascals on top. I would find the 2 things that are equivalent and put the numbers in the appropriate spot. 760 would go on the bottom with millimeters of mercury. 101.325 would go on top. My millimeters of mercury would cancel, and I would know how many kilopascals that same pressure is, just in a different unit. So in addition to temperature having to be measured in Kelvin, pressure is another thing we like to talk about gases with. And pressure, I don't care what unit you use. Most people will use ATM because it's just easier. But you choose. Another characteristic of gas we like to talk about is how much space it takes up, called volume. Volume, as you know, is a 3-dimensional measurement. It will be base times height times width. something we know about those ideal gases is that they always are in motion. They like to spread out as far as possible so that they don't feel any attraction force to any other gas molecule. And we know that the hotter the temperature, the faster the gas molecules will be moving. So to figure out what the volume is of a gas, you would like to know its temperature and its pressure. So what we have learned is that when the temperature is at 0 degrees Celsius, which you add 273 to that, that would be 273 K. And when the pressure of the gas is at sea level, which I don't care, you could call it 1 atmosphere, you could call it 760 millimeters of mercury, you could call it 101.325 kilopascals. But when it's at sea level, and when the temperature is 273 K, we call those exact measurements standard temperature and pressure. It has been determined that when a gas, I don't care what kind of gas, when a gas is at standard temperature and standard pressure, it will take up 22.4 liters of space. If it is not at standard temperature and pressure, it will not take up 22.4 liters of volume. So you need to know the temperature and the pressure that your gas is at in order to tell me the volume that it would take up, how much space it takes up. So when you hear the phrase STP, that stands for standard temperature and standard pressure. The scientists had predetermined that the standard temperature to run these experiments will be 273 K. It will be 1 atmosphere of pressure. So that's your volume. You could calculate by taking the base times the height times the width of your container, because sometimes you won't be able to change the container size, but you'll be able to change the temperature. And what some scientists have figured out is, what do we do if we hold one of these three things constant? Let's say we don't change the volume, but we do change the temperature from morning till night, or we change the pressure from morning till night. What will happen to the other variable? So the three main measurements of gases that you are learning this year is the temperature, the pressure, and the volume that it might take up. Those three are related. We talk about a relationship being direct or indirect. And as I mentioned to you, Torricelli tried to become rich and famous by saying 760 millimeters of mercury climbing up into a test tube could be called 760 torrs. Well, I facetiously say there's three other scientists that also wanted to put their name to fame. And one of them was Boyle. The scientist named Boyle was really concerned about how pressure compared to volume from one scenario to another scenario. What he held constant, what he did not change, was the temperature, and he did not change the quantity of gas. I'm going to put the little letter N to be the quantity of gas. And remember, we measure quantity in moles. So he did not change the moles of the quantity of gas he had. He did not change the temperature. But from one scenario to the next scenario, he played around with pressure and volume. And what he ended up concluding was that the pressure under the first scenario times the volume of the first scenario always ended up equaling what his new pressure was and his new volume was. Remember, he didn't change the temperature. But imagine if you had a balloon and there's gas molecules inside of it and they're putting some pressure on. What if I squeezed that balloon? I increased the pressure. What would happen to the volume? It'd get smaller, wouldn't it? So as the pressure increased, the volume got smaller. So he said, if one of the variables gets bigger, like pressure did, the other variable gets smaller, like volume did, we say that pressure and volume are indirectly related. Some people will say inversely related. It's the same thing. That means as one gets bigger, the other gets smaller. So if you ever question, hey, how are pressure and volume related? If you can remember Boyle's formula, just make up numbers. Say, okay, my pressure is 1, my volume's 10. And I increase my pressure to 2. Well, 1 times 10 is 10, so the left-hand side was 10, and if it's equal, the right-hand side's got to be 10. So what would the new volume have to be? It would have had to have been 5, right, for 10 to equal 10. So as the pressure got bigger, the volume got smaller. They went in different directions. That's called an indirect relationship. Then along came a guy named Charles. Charles was also curious about those 3 characteristics of gas: pressure, temperature, and volume. But this time, Charles kept the quantity the same, and he kept the pressure the same. He did not change the pressure. He did not change the amount of the gas. But what he did change was temperature and volume. And what he found is that as he increased the temperature, the volume got bigger. And that should make sense to you, because I told you temperature measures kinetic energy, how much the gas is moving. If you increase the temperature, they're going to move faster and they're going to spread farther apart. They're going to take up more space. And he found that temperature and volume have a direct relationship. From one scenario to the next scenario, here, I'll put this in a different color. He found volume 1 divided by temperature 1 ends up equaling volume 2 divided by temperature 2. And that is called a direct relationship. Directly related. And then another guy, hyphenated last name, Gay-Lussac, he held volume constant and the quantity of gas constant, and he just changed the pressure and the temperature. And what he found from one scenario to the other, the pressure and the temperature the first time equaled the new pressure divided by the new temperature the second time. So those are the 3 main gas laws. Law in chemistry means a formula that we use and it's not been disproven. So nobody's disproved this relationship. Nobody's disproved Charles' law. Nobody's disproved Gay-Lussac's law. Be prepared for me to ask you, hey, how are pressure and temperature related? And your answer would be directly related. How do you know? Well, you know Gay-Lussac's formula, P1 over T1 equals P2 over T2. Make up numbers. If pressure is 1 and temperature is 10, and you change the pressure to 2, how do you get the left-hand side of this equation to equal the right-hand side of the equation? Because remember, nobody's disproved this yet. So assuming it's true, how would you get 1 over 10 to equal 2 over x? Well, that would have to be 20. And as pressure got bigger from scenario 1 to scenario 2, so did the temperature. As they both go in the same direction, that is, if they both increase or they both decrease, you say those variables are directly related. If they go in opposite directions, you say they are indirectly related. So the 3 formulas, if you're taking notes, that you should really know are Boyle's law, Charles' law, and Gay-Lussac's law. Now, do you need to know them by name? Well, I would advise it. But then some other scientist said, you know what? I don't need my name to a formula. Why don't we just put all of these formulas together and come up with what we call a combined gas law? And I'll tell you what, that's really nice. The combined gas law just says P1V1 over T1 equals P2V2 over T2. But that does assume that the number of moles of gas were held constant, that you didn't change the moles of gas, which is a fair assumption. So in all four of these formulas, we didn't change the quantity of gas. But here it still holds true that pressure and volume are indirectly related. Pressure and temperature are directly related. Volume and temperature are directly related. They just put it all together. And that's called the combined gas law. So in a story problem, in your homework, I could give you that in the morning, I had gas at, not me having gas, but my gas was at a pressure of 0.96 atm. So I would write P1 equals 0.96 atm. And I could tell you that it took up 2 liters. And then I could tell you the thermometer read 20 degrees Celsius. I've got to be careful here though, because in any one of these formulas, temperature must be in the unit of Kelvin. So when I write this out, I right away add 273, and I say that's actually 293 K, and then I put a line through it. Because I show my work, but I just want you to understand where my 293 came from. So I could tell you, hey, in the morning this was the situation. But gosh, in the evening, the new pressure was 1.1 atm. I don't know what the new volume was, but I know that the new temperature was 22 degrees C. So again, I'm going to add 273, and I'm going to get 295K. Okay, so if I want to know what the volume was in the evening, maybe I'm talking about a helium balloon or whatever. If I want to know what that new volume is, I simply just fill out this formula. P1 is 0.96. Volume is 2 liters. Temperature in Kelvin is 293. That should equal the new pressure, the new volume, which I don't know, and the new temperature. And then I would do my math. On the calculator, I'll do the left side. And on the left side, I get 0.00655. On the right-hand side, I get 0.00373 V2. So to get V2, I would divide both sides . And when I throw that in the calculator, I get 1.76. 1.76 what? Liters. Whatever unit this volume is in. Remember, I don't care what unit the volume is in, but whatever unit it is in the first scenario, it must be the same volume or the same unit on the second scenario. So since this was liters, my answer is liters. So that's how you will solve any of these gas problems in chapter or lessons 29, 30, and 31. And that's the basics to gases. I'd like to take you one more step to one more law of gases called the ideal gas law. We've already talked about an ideal gas. But what's the ideal gas law? Well, if you notice, these other gas laws I've shared with you are comparing one scenario to another scenario. And it was proven through experimental work that from one scenario to the other scenario, these will be equal. But what if you're just in one scenario? What if you're just in the morning and you don't know one of the variables? Could you solve for it somehow, some way? And the answer is yes. There is another equation called the ideal gas law. And that formula takes all four things that we like to talk about with respect to gases: the temperature, the pressure, the volume, and the quantity of gas. That equation goes like this. The pressure times its volume should equal the quantity of gas in moles times some gas constant, which we use a capital R to represent, times the temperature in Kelvin. So you already know about pressure, you already know about volume, you already know about temperature, and I told you that N represents the moles of the gas. So what is R? I call R just a fudge factor. If your pressure is measured in atmospheres, your pressure must be in atmospheres, this is a gas constant, which would be equal to 0.0821. Now, that's if it's in atmospheres. Now, how? Why? Well, if this is in atmospheres, to use the ideal gas law, your volume must be in liters. And that's why I told you most people will use liters to measure volume in. Because if you do the ideal gas formula, your volume has to be in liters. We've already said N is moles. And we said temperature is Kelvin. What is the unit for R? Well, if you solve to get R alone, you would divide both sides by NT. Or you would end up with atmospheres liters divided by mole Kelvin. And that would give you the unit for this gas constant. So the unit for this guy is a goofy unit. You just write what you have here. You'd have ATM times liter divided by mole times Kelvin. And that would be the unit for that gas constant. But to use 0.0821, your pressure must be in atmospheres. If I give you a pressure in kilopascals, that fudge factor is not 0.0821. In fact, that one is 8.314 if the pressure was in kilopascals. The volume would still be liters, the quantity is still mole, and the temperature is still Kelvin. So you have to pay attention to what unit the story problem gives you the pressure in. If you don't want to memorize a bunch of different constants, and there's another one, if the pressure is millimeters of mercury, it's 62.4. But if you don't want to memorize these other ones, the ones that most students will memorize is this one. They'll memorize that because the pressure's in atmospheres. Remember we saw earlier that the unit for pressure that was the easiest to manipulate was atmospheres, because one atmosphere equaled everything else. So I would suggest to you, if you want to know another formula for gases, which is a very popular one, it's called the ideal gas law. It's PV equals nRT, knowing that the units have to be liters, have to be moles, have to be Kelvin. The value of your gas constant depends on the unit you chose for your pressure. I would suggest atmospheres and then just memorizing this number, 0.0821. The reason I wanted to branch off in this chapter and share that with you is because when I first met you, I taught you about a mole, or you were learning about a mole, and we worked on how to convert to and from mole. I want to show you how we can now also convert to and from volume. You don't have to watch me erase. So you remember this graphic I gave you before? I said the word mole, the unit of mole, is the main clearinghouse in chemistry. We often want to quantify things in moles. Even if we're given the mass of something, we have learned that if we go to the periodic table, we can get what 1 mole of that substance weighs by taking the average atomic mass from the periodic table. If we're given the quantity, like how many atoms or how many moles or how many shoes or how many pencils, we can convert that to a mole and go back and forth by using Avogadro's number, 6.022 times 10 to the 23rd. Well, now I'm going to show you how we can talk about moles if I give you the liters of a gas. We can go back and forth to volume. Measured in liters, but it has to be gases only. And that number we're going to use is 22.4 liters equals 1 mole. So we now can go from, hey, I've got 2 liters of hydrogen gas. How many atoms do I have? Well, I could go from liters to moles, moles to molecules, molecules to atoms. Because remember, the hydrogen is a diatomic element. I could say, hey, I have 16 grams of carbon dioxide. How many liters will that take up if, notice this, asterisk, and only if and only if you are at standard temperature and pressure. You can say that 1 mole of gas will take up 22.4 liters if I was at 0 degrees Celsius and 1 atmosphere of pressure. So if I took those 16 grams of carbon dioxide and I wanted to know how many volumes it was taking up, I convert grams to mole and then mole to volume. And you might question, well, what if? Mary, what if I'm not at standard temperature and pressure? Then how many liters does 1 mole of a gas take up? Well, I'm going to show you the beauty of knowing that other formula called the ideal gas law. Remember, it's PV equals nRT. 22.4 liters comes from that equation. Now remember, 22.4 liters is how much space 1 mole of gas will take up if you are at standard temperature and standard pressure. The ideal gas law formula says if you are at standard pressure, so that was 1 atmosphere, I don't know the volume, but if I have 1 mole of gas, and since I'm measuring pressure in atmospheres, my gas constant has a value of 0.0821. And my temperature, well, if I'm at standard temperature and pressure, standard temperature is 273 on the Kelvin scale. Temperature must be in Kelvin. When I throw that into my calculator, 0.0821 times 273 divided by 1, I get a volume of 22.4 liters. And that is how we're able to say that 1 mole of a gas, any gas, if it is at standard temperature and standard pressure, know those values, it will take up 22.4 liters. If I give you a story problem where I don't have it at standard temperature or I don't have it at standard pressure, let's say that this is 0.096. And let's say the temperature was 300. So it's going to be hotter, which tells me it's going to be moving faster, probably taking up more space. Plus, it's under less pressure. So the less pressure a gas is under, it's going to take up more space too. Let's find out what the volume of 1 mole of gas would be under these conditions. My gas constant stays the same because I didn't change the unit of pressure. So I'll throw into the calculator 1 times 0.0821 times 300. I'll divide it by 0.96, and I get 25.65. So when I punch that in the calculator, I get 25.65, and I'll put that right there. So that means that when I have 1 mole of gas at this atmosphere and this temperature, it should take up 25.65 liters of space or a volume. So if I had asked you, given those 16 grams of carbon dioxide at 0.96 atmospheres and 300 Kelvin, how much space would that take up? Well, that means I have to convert from mass to mole to volume. So starting with the mass at 16 grams, I would write 16 grams of carbon dioxide. I put it over 1. I want to convert from mass to mole. And I know from the periodic table that 1 mole of carbon dioxide is the same thing as 44 grams of carbon dioxide. Now to go from mole to volume, I want to convert, but I have to stop here because the conditions are not the one I have memorized. I know it takes up 22.4 liters if I'm at 1 atmosphere and 273 K, but I'm not. So since I'm not, I've got to stop here. I have to go to the ideal gas formula, put in my conditions, and solve for the volume if I have 1 mole, like I just did. So I know that carbon dioxide, if I have 1 mole of it, it will take up 25.65 liters if I'm at 0.96 ATM and 300 K. So now that I know that, I do have a ratio. I have 1 mole of my gas, in this case it's carbon dioxide, should take up 25.65 liters. And then the moles of carbon dioxide cancel, the grams cancel, so my final answer will be in liters. And when I throw those numbers into the calculator, I get 9.33 liters of carbon dioxide. So what's that saying? It's saying if you gave me 16 grams of carbon dioxide at that pressure and that temperature, it would take up 9.33 liters of space. So I know I threw a lot at you. I hope you understood it. I hope you found it educational. If there's something you didn't understand, please go back and replay the video. Stop and pause it at different points along the way. On the PSL page, I will give you a few homework assignments. Most of them will come from your book. I will give you a few conversions. Again, converting from the atmospheres into kilopascals or millimeters of mercury into pounds per square inch. I'll give you some pressure conversions, as well as I'll give you some conversions going this way to and from a mole. But a lot of that is in the homework in the book. So if you have any questions on this, just go back, replay the video, try your homework. I'll supply the answers. If you have questions after that, ask me in class. All right, hope everybody's staying safe. Be careful.